Hey everyone, Viraj this side. Welcome to my channel. This is the first video on my channel, and in this one I'll be proving that Euler's constant E is irrational using Taylor's theorem. So firstly, let us quickly review what exactly is E. So we defined E in a couple of ways. The first of which is that it is the base of the natural logarithm. So we know that the natural logarithm is defined by this integral, and the we define the logarithm, we write the logarithm as this, and when the base of this logarithm is e, then we say that the logarithm is the natural logarithm ln x. And so for this particular base, which is also defined as this integral, we say that it is the Euler's constant is this base of the natural logarithm. We also define e using a couple of sequences. So we do know what sequences are. It is a function from natural numbers to real numbers. So the first of these sequences is this one, which is the limit of 1 plus 1 by n whole raised to the power of n as n tends to infinity, and this converges to e, as does the limit on the right, which is a limit of n tends to infinity, the summation of 1 by k factorial from k is equal to 0 to n. And if I just write this out, it is 1 plus 1 by 1 factorial plus 1 by 2 factorial plus, and all the way to n. And as we tend n to infinity, we get that this expression also tends to e. And using these expressions, we can also figure out the bounds for e. We get that e lies between 2 and 3, and you are probably also aware that e is approximately 2.71, but right now we're not concerned with the exact value of e. We are only concerned with proving that e is an irrational number, i.e. this decimal expansion does not terminate. So let's get to the proof, but before that we also need a prerequisite, which is Taylor's theorem. So uh, we come to Taylor's theorem. So what exactly is Taylor's theorem? So I'm just going to go over it a bit broadly, and if needed, we can discuss it in a future video as well. So Taylor's theorem gives an approximation of an n times differentiable function, or I should have said n plus 1 times, so that's a bit of a typo, but yeah. So it gives the approximation of an n plus 1 times differentiable function around a point x equal to c. So we try to approximate functions using polynomial functions. So as you can see, these are on the right hand side, these are all polynomial functions, and uh, we and fx approximated around c is given as fc plus f dash c into x plus f double dash c x squared by 2 factorial plus, and you can see the pattern, and the nth term is actually given by fnc. It means that f differentiated n times and into x to the power of n divided by n factorial. This is also the nth degree Taylor polynomial. And there is also though a remainder term, because you cannot exactly approximate a function using simply an x you cannot exactly approximate it using simply polynomial functions. So definitely there will be some difference between the actual function and the nth degree Taylor polynomial, which is given by this f n plus 1 xi x to the power of n plus 1 divided by n plus 1 factorial. And xi here is just some arbitrary number which lies between c and x, between c and x, or x and c, as the case might be, whichever is bigger, whichever point we choose to approximate the function value for. Okay, so now that we know the basics of Taylor's theorem, we can move to proving exactly how E is irrational. So for this proof, we are going to be applying Taylor's theorem to e to the power of x in the interval 0, 1. And so let us quickly write down what this is going to look like. So our fx is e to the power of x, and we can clearly see that f of 0 is equal to f dash 0 is equal to f double dash 0, and it is equal to all of the derivatives till the nth derivative. which is equal to 1. This is because d by dx of e to the power of x is simply e to the power of x, right? So using this, we get that all of the derivatives are equal to 1, except for the n plus 1th derivative, which we are finding at some arbitrary point xi or c, where c belongs to um, 0, 1, right? So fn plus 1 c is not going to be equal to 1. It's going to be something arbitrary, which is e to the power of c, right? So we'll just put x equal to c here, and we'll get e to the power of c. So what does our nth degree, what does our Taylor's series of e to the power of x look like? So it becomes 1 plus x square by 2 factorial plus x cube by 3 factorial plus dot 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 till x to the power of n by n factorial plus e to the power of c x to the power of n plus 1 divided by n plus 1 factorial. So now what we are gonna do here is that we're gonna put x equal to 1 in this expression. So what we're gonna get is that e is equal to, and it's pretty natural to put x equal to 1, right? Because we are concerned with e. So that's what we're gonna do. So we're getting 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial up till 1 by n factorial plus e to the power of c into 1 by n plus 1 factorial. So this is what we're going to get. And now, as the slide does say, is that we're going to prove by contradiction the fact that e is irrational. So in a contradictory proof, what we do is that we assume that e is rational. What that means is that therefore e is equal to p by q, where p, q are coprime, and q is not equal to 0, right? That's what it means. So let us substitute this value of e back into the earlier expression which we had. So what we get is that p by q is equal to 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial up till 1 by n factorial plus e to the power of c by n plus 1 factorial. So what we're now going to do is that we're going to multiply both the sides by n plus 1 factorial. Okay, so what this does is that it isolates, or rather instead of this, what we'll do is we'll multiply it by n factorial. Cool. So what this does is that it gives, on this LHS, it gives us n factorial into p by q is equal to, we get n factorial times 1 plus 1 plus 1 by 2 factorial plus 1 by 3 factorial up till 1 plus 1 by n factorial plus e to the power of c by n plus 1. Now note that, and I kind of skipped over this, that n factorial is simply 1 2 3 up till n. I hope you did know that. If you didn't, sorry, but now you can follow from this point onwards. So now note that since you know this definition, it just means that when you multiply n factorial with all of these terms, you're going to get an integer. So this whole term, when you multiply it out, it's going to be some integer, which for like m belongs to, and in fact not just an integer, it's going to be a natural number. Cool. So what I'm going to do is I'm going to write this as m, and I'm going to take it to the left hand side. So what I get is I get n factorial times p by q minus m is equal to e to the power of c divided by n plus 1. Alright, now just note that m, this number m, which I have written out here, it's going to be definitely smaller than this quantity, because the quantity on the right is always positive. And suppose, and now I have the liberty to choose n, right? Because n is the like e to the power of x is infinitely times differentiable. So I am at liberty to choose n as large as I want it to be. So suppose I choose n to be greater than q. So what happens when I do this? when I choose n to be greater than q, what this means is that when I write n factorial, I'll write 1, 2, 3, then I'll somewhere come to q, and then I'll go on further until I reach n, right? So, and since of course since p, q are co-prime and they are uh, natural numbers, integers, so definitely we're going to get to q before we get to n. So this number on the right, for n is greater than q, this factor is going to get cancelled, and this is going to be a natural number, and we know that this is greater than m, so this whole thing is going to belong to natural numbers. This is going to be a natural number. But just note that on the right hand side, this expression, so think of some n which is you consider this expression for very large n, for very large n. So what is going to happen to this as n tends to infinity? This expression is actually going to tend to 0, right? This expression is going to tend to 0. But we know that this LHS is always a natural number, but the RHS is tending to 0 as n tends to infinity. So if you don't want to think of it in terms of infinity, just think that if we make n large enough, this e to the power of c by n plus 1 is going to become smaller than 1, and 1 is the smallest natural number. So therefore for all n, this cannot hold because 0 is not a natural number. So here we have our contradiction, and this is via this contradiction, since we had made the assumption that E is rational, this is violated. Therefore, we can conclude that E is definitely an irrational number. So there, this was a pretty nice proof. I think there are several other ways to prove that E is irrational. Euler himself he proved that E is like an infinite fraction. He wrote it as an infinite non-terminating uh, like he calculated it to 18 decimal places and all. So yeah, that is perhaps a content for another video, but yeah, I just wanted to share this proof with you because I found it interesting and I had recently studied Taylor's theorem. So yeah, I hope you did like this video. If you did, be sure to like, subscribe and comment, and do leave some suggestions if you think I should make more videos on topics, and do suggest topics on which you think I should make more videos on. So yeah, I hope you enjoyed, and if you have any other suggestions, be sure to comment them down below. Thanks.